Who does it?
Computer when it's idle.
It's not idle.
No, relative idle. It's never.
Is this the graphics course here? Is this is it?
You have time.
Poli-sci 1. Painting programs in Poli-sci 1.
I thought this was abstract economy theory. I was in your class.
That one way back I taught here?
No. I was talking junior high school.
I met a guy in Santa Cruz a couple of days ago. I was down there, and he said, "Hey, I took that class that you taught at Berkeley." God, that was a former lifetime. I had to break a leg to come here this time. Get out of Professor Hood, throw it all away, get into something interesting like color, you know. Making pictures. Is this a credit course?
Yes. They haven't approved it yet, though.
Oh, I see.
It hasn't been approved yet. One of these days I'll get his class cards.
Well, is that why we don't...
Somebody asked me about class cards. I don't know a thing. Can't help you on
We
that.
understand.
Okay. Yeah.
Oh, you added those?
Yeah.
Oh, is that how we're supposed to...
Where'd you get your Saturn shirt? Oh, I thought maybe you had something to do with JPL or flyby. Yeah. Yeah, it's nice down here. Are you going to give me a cue when we're ready to go? We're ready to go. Okay. All right.
You are on.
Okay. I'm Alvy Ray Smith. I'm taking Ed Catmull or Jim Blenn's place today because the two of them are both in Washington, D.C. at the Library of Congress at some kind of symposium. The Library of Congress has organized to teach congressmen what is available at the library. So Ed has asked me to speak to you today about paint programs and closely associated things like filling and color space models. I think that you've already had one term of this course, is that right? That you are probably getting to some more serious stuff now, like I think it was polygon tiling last week. Yes, no? Please talk to me even though we're on TV. Okay. What I'm talking about is probably a little more basic, a little lower level stuff, more elementary in graphics than polygon tiling or quadric surfaces or bicubic patches or some of the hidden surface algorithms or some of the other things you'll get to in this term, I suspect. I understand you have not discussed texture mapping yet. I'm not going to discuss it today, but one of the things you need to do texture mapping is a texture. Where can you get textures? There are several sources. One is you can scan it in from the outside world. Just take a real picture, digitize it, and use that as a texture. A texture is just, in my parlance, or computer graphics parlance, a two-dimensional set of pixels. It could be anything. It might be a picture of something, or it's a visual texture, not a tactile texture. Okay. Another way to make textures is to generate them algorithmically. Most algorithmically generated textures up until this last year were fairly sterile. Not to say there isn't a vast world of them to be explored and discovered yet. Last year, Lauren Carpenter and a couple other fellows from Texas came up with the notion of generating fractals. You familiar with fractals? Seen the book by Mandelbrot? It's a beautiful book. I'm not going to talk about fractals today, but it turns out to be an incredibly rich algorithmic way to generate textures of natural complexity. Lauren is with us over at Lucasfilm to help us generate some astonishing landscapes, we hope.
Can we have a field trip?
Well, I'll tell you, we got our first frame buffer this last week. It's an Iconis frame buffer. We started seeing color pictures at long last after a year and a half of planning. So right now is probably the best time of all to come see, although don't come all at once, please. Before we get geared up, close the doors because we're in production, things like that. Now, the painting program is another way to generate textures where you just simply hand paint them. The classic, in a computer simulation of classic art of painting with oil on canvas or acrylic on canvas or whatever on whatever. I'm going to be talking a lot about frame buffers, color maps, cursoring, tablets. I'm not sure that all of you are familiar with those. I think you are, but I might go over them very hurriedly just to say the words that I want to assume you have heard at least once. How many are familiar with frame buffers? Can I just have a show of hands? Okay, color maps? Okay, tablets? All right. Okay.
Once you ask the compliment.
No, I could see the compliment. It's not that big a group set. Well, very briefly, when I say frame buffer, I mean what I think you all mean to be a 500, well, let's say it's a piece of computer memory. Leave off any resolution requirements. It's a piece of computer memory, just fairly ordinary computer memory, with the addition of one thing, and that's a piece of circuitry, electronic circuitry, to let us look in and at the contents of that memory at video speeds. In other words, 30 times a second, we get a sample of what's in that memory. And the way that's done is the video controller rips across in raster order, that is row by row, going down the memory, assuming it's organized in a two-dimensional fashion. It pulls out a value in the memory and assigns a color to that value somehow, and sets the three guns of the color monitor to the color it determines. Then it goes to the next pixel, a term I assume you all understand. Grabs the value, assigns a color, etc. Very fast. Typical off-the-shelf frame buffer these days is nominally 500 line resolution. It's a raster scan cough. There are some home frame buffers, home hobbyist frame buffers that go from 64 line resolution up to 500 line resolution. And you can now get frame buffers of even higher resolutions, 1,000, 2,000 on up, although they certainly aren't off-the-shelf items yet. We will of course use a higher resolution frame buffer than 500 line when we get around to generating films frames for movie film. Unknown what resolution that is at this point, however, but I'm pretty sure it's higher than video. Okay. Okay, so the other thing we need, how do you assign the color? Well, the easiest way is to, or one of the very easy ways is to take this value, maybe an 8-bit value out of the frame buffer, out of each pixel, and do a table lookup. That's the so-called color map. Color maps, well, I can't say typically, but I will. Typically, they have 8 bits for each of red, green, and blue. In other words, 24 bits to specify the color attached to any one value in the frame buffer, any one pixel value in the frame buffer. Our Iconis frame buffer at New York, well, all the frame buffers at New York Tech, where all three of us came from at one time or the other, had 12 bits per primary, so that was 8 bits in and 36 bits out, look at color map. The Iconis has 8 bits in, 10 bits out per primary, so 30 bits out. 8 bits is probably enough, although there are arguments, per primary I mean, although 9 or maybe even 10 bits is better for film because you have to take care of nonlinearities. Okay. The nice thing about color maps is you can change the whole color, the color of an entire frame, just in an instant, as far as we're concerned. You drop it into the vertical interval, the point where the electron gun jumps back to the top and starts its rastering down the screen again. In that little chunk of time, you drop the color map change in, and as far as we're concerned, it changes instantaneously. I'll also talk about I'll talk about color mapped frame buffers, and I'll talk about RGB frame buffers. Color mapped frame buffer is what I've discussed so far. It's got 8 bits per pixel, typically, and those 8 bits are color mapped into the color you see on the video display. A richer frame buffer has more bits per pixel. For example, 24 bits per pixel. Instead of looking up the color in a color map, you just read the color right out of the frame buffer because you have 8 bits for each color right at the pixel. What that gains you is a vast number of colors which you can see at any one time. With a color map system, you can only see, in an 8-bit frame buffer, you can only see 256 colors at any one time. It's not very restrictive because you can set that color map to be to hold any colors you like from a space of billions. 68 billion, I figured it out once. It depends. That's on a 12-bit, on a 8-bit in, 36-bit out color map, it's 68 billion colors. Okay. Yeah.
Slightly incidental point, but I've heard it said that film has a narrower color range than video, and that we have this perception of film as being more real because of something about the limits of the color values that you assumed in film. Is that true?
I'll talk about that today. I wouldn't say it's narrower, it's different. It's a different set of the human perceptual space, and it might be smaller, but I haven't seen that's a hard one to grab hold of. It's hard to know exactly what the film color gamut looks like. I'll show you what I know later. Okay. In a 24-bit frame buffer, you have, well, 256 cubed colors possible. Well, that's more than you can see on a screen since they're only, it's 512 squared roughly, pixels on the screen. So point is you can set every pixel to a distinct color, and that's very rich. Have any of you ever worked with a 24-bit, or as we call it, an RGB frame buffer? Have you ever worked with an 8-bit frame buffer? Let's start there. Has anybody worked with an 8-bit frame buffer? Yeah. They're a lot of fun. I've worked with them for years, but once you get to an RGB frame buffer, then things get astonishingly better. For one thing, when you start doing shaded surfaces, colored shaded surfaces, you have to have all those shades of all those colors. And the number of colors, 256 sounds like a lot until you start thinking about all the shades and all the tones of a given hue and the desire to have many hues. Okay. Another thing about frame buffers, they nearly all come with color maps. Another thing they sometimes come with is a hardware cursor. A cursor is just a device or a little pattern that shows you where you are on the screen. The notion being that you're using an electronic stylus on an electronic tablet, and you all say you're familiar with that. You're down here working on the tablet, but you're looking up at your monitor. What is it that you're looking at? How do you know where you are? Well, there's a little cursor on the screen that always tells you where you are. If you don't have that cursor, then it feels very unnatural. Bad human interface. Now, the way to do the cursor, you could program the cursor in. You could write the cursor every time you moved your stylus. You could unwrite the last cursor, rewrite the new cursor, having remembered what was under the last cursor so you could restore it. And it's possible to do in software to do cursoring, but it is a tedious, boring, cycle-stealing task. So most modern frame buffers have a hardware cursor, which is programmable. Its shape is programmable typically. And it either complements into the memory, so that just with another complement you can restore what was there, or it is a video mix, which, in other words, it doesn't destroy what's in the memory at all. It's downstream from the memory, strictly video. The one problem you have to watch out for with cursoring is that the color of the cursor does not disappear in the color of the object being cursored over. There are quite a few tricks. One is the complementing cursor, which complements what it's over. Sometimes lose that too, but not so often. And then the ability to change the color of the cursor, of course, is a way to, if you somehow can detect what the color is you're writing over, you can change the color of the cursor and always see the cursor. Okay, and then the final little element that I want to be sure we've covered is tablets and tracking. We've already discussed it here. The notion, I'm sure everybody knows, that a tablet is a slab, and you have a fountain pen-like device, and you move with no pressure with your fountain pen, your stylus, across this tablet, and the wire going off to the computer tells the computer an XY coordinate pair corresponding to where you are on the tablet. It's a way of getting 2D information into a computer. It's very natural too. It's although there are a lot of devices to interface humans to graphics machines, the tablet is by far the richest anybody's dreamed up yet. You can simulate knobs, you can simulate joysticks, you can simulate trackballs, you can simulate all the other ones on a tablet. Plus you can do things like draw and have paint programs. They usually have a little switch in the tip, and when you press down on that switch, you set a bit. When you let up on the switch but don't remove the pin from the surface, in other words, you're just letting it rest on the surface with no pressure, another bit is set, called the proximity bit. So you can be in proximity, or you can be proximity and in pressure, all combinations of those two bits. Typically there is a cursor that's been programmed somehow or another to follow you around as you track. It's called tracking the tablet. And if it is correctly done on a non-time shared system, very important is that when you're doing real-time interaction with a machine, you're not getting swapped out every few seconds. And on a fast enough machine, the cursor appears to move rigidly when you move and in proportion to the way you move, and so the transfer from down here to up here space is instantaneous and usually requires no thought. I belabor that point perhaps because I run into it time and time again trying to explain to people what it's like to paint, and they can't mentally, without seeing a painting system, jump from working here to having it happen up there. As I've pointed out many times, we had a class of certified morons come through New York Institute of Technology one time, and they picked it up just like that. So anybody can do it. Okay, painting is a very simple notion. In fact, it's probably a misnomer. The misnomer serving the purpose of seducing people into the world of computer graphics who might not ordinarily be attracted to the space. The basic notion is that is local modification of a picture under human control, under hand control, in fact tablet control, or some other kind of input device, but usually a tablet. And it could be this local modification of the picture might simulate what we call painting, and then in fact is where the name comes from. I'd like to list off some of the other things you can do. Well, you can do any modification you can think of to a picture you can do and call it painting, another type of painting if you want. Basic notion is you have a brush. What's a brush? Well, it's a shape. It's a two-dimensional shape. Typically a brush is not as large as the picture you're painting on, but it could be. Before I go any further, in fact, let's just show a videotape. It's about a 5-minute videotape of a painting program. Now, this tape doesn't have sound on it. It begins with me standing in front of a typical paint station, a large tablet, an RGB color monitor, a standard television console, and a Tektronix 4014 just to its right as you're facing the, there it is, the Tektronix 4014, although you can't see it, contains the menu. That is the list of the items which can be selected and used in the paint program. I, in fact, have a menu right here. I don't know whether we can see it on the over... Can we switch back and forth, or is that inconvenient to the overhead projector? I'm not sure people in television land are seeing that, but this is what the this is what the menu screen has on it. This little arrowhead-shaped thing right here is the cursor, which moves around as I track. And if I put that cursor over, the sketch button, for example, and press down, I go into sketch mode. Okay, let's go back to the videotape. Now, what you see here is not me, by the way. This is Paul Zander, a background artist, a conventional background artist from animation, who is completely computer naive and is doing the painting, a typical painting, to show off the paint program. He's doing this one very quick and dirty, taking about 20 minutes total to do it. I've edited it down to about 5 minutes, and only a 500 line resolution. He normally paints at 1500 line resolution. It takes maybe a couple hours or sometimes a couple of days even to do a painting. He's a real fan of computer painting, by the way. After being so frightened he literally could not move the first time he was confronted with it.
Does he work for Lucas?
No, he works for the New York Institute of Technology, or New York Tech as I will call it frequently. You may have seen the palette come up across the bottom of the screens a few times. It's an array of the current color map. This is an 8-bit frame buffer you're looking at. This is video right out of the frame buffer. He could choose, there's the palette. He can move his cursor over to any color he chooses, and when he presses the stylus down, he gets that color. It's attached to his paintbrush. What he's doing there is filling. He touched an area, and I'll discuss filling in a little more detail. He touches an area, and every pixel that is edge connected to the pixel he originally touched and of the same original color gets changed to his new color, the one he chose off the palette. Incidentally, he doesn't have to choose a color off the palette. He can just go up on the screen anywhere and grab that color. Now, this looks fairly crude so far, and that's because he's using a great big fat brush, maybe a 9, I think it's a disc about 9 pixels across, just to rough out the picture. If you kind of keep in mind how crude it looks now, and by the time we get to the end of the tape, we'll have transformed quite a bit as he hones it into shape.
So there's a separate input device to control the 4014?
No, they're both being run from the same tablet.
Okay.
And just by a graceful, a swipe of the hand, just very easy, you can go into a special area on the tablet, which happens to be any of the margins of the tablet in this case, just like this, and it switches from one space to the other. Well, now those trees are a brush. A brush, like I said, is just a little picture, a little two-dimensional shape. It can have color attached to each of its pixels, and in this case it does. He happened to paint this picture of a bunch of trees. I guess he has 2 different pictures there. The night before this taping, and saved it. You can save any little picture you want as a brush, and on the menu I showed you there was a thing called Save Brush. And it, yes, complementing cursor. You can see it complement as he moves. It's also a hardware cursor, and this happens to be an Evans and Sutherland frame buffer you're looking at. All right, now here, the brush in this case, anybody want to hazard a guess about its shape?
A lot of little points.
Yeah, it's a random cluster of dots, fairly widely spaced, and as he tracks in pressure on the tablet, each dot leaves a trail behind it. Grass, voila. So a brush doesn't have to be connected. I guess I should say something about the notion of transparency. When you save a little picture on that screen, of course you're saving, well, you save a rectangle. It's a lot easier to save a rectangle. But you can also specify that a given color or colors in that rectangle be treated as transparent. In other words, when we restore that picture into the brush, into the frame buffer, we just simply don't write the ones that are designated transparent. It's very simple. Now, the brushes you've seen so far have all been small. There's been the 9-pixel disc. There's the little cluster of random pixels that form the grass brush here. The 2 rubber stamp forest brushes. But a brush could be the entire screen. You could pick that whole picture up and paint with it. It would be a little slow, but it would work.
What's the direction of those dots?
Video edit there, yeah. The direction of the dots just is the direction he goes. Yeah. Once again, he's painted some flowers the night before, saved the brush, and one of the items on the menu is Pick Brush. When you hit that item, over on this display, the text monitor comes up a list of all the brushes that are available that people have made. At New York Tech, there were hundreds. He searched through it until he found flowers, or whatever he called it. Chose that, and it became immediately attached to his stylus.
What do you got me for
Now that rectangular cursor, when he presses down, what was inside where he pressed down gets magnified to fill the screen. That's another typical frame buffer hardware feature that is available these days. That was a magnify simply by a factor of 2. It doesn't change the contents of the memory, it just changes the video timing so that you can think of it as replication of the pixels to get a blow up by 2. You can get blow ups to up to 16 or even further sometimes. What he's doing now is he's painting that little set of bricks. He surrounded them with a couple of window cursors, and he's saving that set of bricks as a brush with the castle color as transparent. Now he's rubber stamping, as we call it, with that brush he just made.
Now, if this brush were off to this, weren't centered on it, like it was on the edge of the castle, you would get bricks off. And
you sure would. Yeah. It doesn't know about it's just a piece of memory, and you're writing in. And by the way, when you write, you overwrite. You're writing into memory here. So if you don't take care to save what was there before, it's gone forever. You can always erase. Erasure is trivial. Just choose the color you want to. Like if you want to paint out of bricks, you'd choose the castle color and just paint out the bricks. It's perfect erasure. Or he could have saved the picture several steps back. There's a button. You can always save the current picture. And that's a frequent habit. Whenever you are afraid you're about to destroy your world, save the picture. It doesn't hurt. You can get rid of the copies.
Can you see what it looks like?
Very many big discs, yeah.
How big?
Well, we had, it seems like it was 12 to 15, something like that, RPO6s with lots of packs to swap in and out. And these are only 8-bit pictures, recall. When you get to 24-bit pictures, in higher resolution, the disk space required is immense.
Suppose you're rubber stamping a picture. Can you see what it's going to look like if you were to put this one in?
The cursor, I don't know whether you noticed or not, but the cursor that appears, I believe Paul always used the standard triangle. You could always have that if you like, but if you wanted to, you could flip a bit somewhere, and the cursor would be the shape of the brush. Okay, which is the one I use. Yeah, that's the one I like to use. It was not a hardware cursor, however, and it was being done in software, so it tended to beat with the Evans and Sutherland frame buffer did not have a way of grabbing hold of the vertical interval to let you drop to synchronize your painting with the vertical interval, so we got beating. This is the same artist, but in a different space of colors. I'd like to emphasize that although what you see is kind of a flat, cartoony type of painting, that's because that's Paul Zander. It's his style. He's been doing this style for years. You get another artist in here, and what you see is his style. He called in a simple reflection program. You can hack those out in about 5 minutes. And that's the man. And that's the place. Very good graphics laboratory there. Yeah. Okay, that's the end of that tape. Now that went by fairly fast. I'd like to kind of elaborate on a few of the things that we saw there. There was simple painting, which means you take the form of the brush, assign a color to it, and choose a color. And as you lay down, whiteboard. Here's our frame buffer, let's say. Suppose your brush is this shape right here. As you track, there's a cursor moving around that lets you know where you currently are, as usual. And sometimes, like I was just saying, this cursor might actually be the shape of the brush itself that you're about to use, or it could be that little triangle or whatever your favorite cursor shape is. This was the triangle, the upturned V, the upside down V was the favorite cursor. It's my favorite cursor, I'll put it that way. Okay. The brush defines the local area of the frame buffer that you're going to modify. And that is, in fact, the painting paradigm, or whatever you want to call it. Under hand control, you move around an indicator of what you're going to do in a local area to a picture, and what you do can be anything. In painting, or the simulation of painting, what you do is just take the color that you've chosen and write it in. Just wipe out anything that's there. It's one of the most trivial. It's a write, complete word write. More interesting types of painting look at what's underneath that brush and combine it with what's in the brush to do fancy operations. For example, you might have a brush that had a cross section like this. Suppose it's a half of a sphere. It looks like this from above, but it's got values in it to indicate its height at each point. Then you might use each one of those height indicators in the brush to weight how much color was added to the picture under the brush. Okay? What you get there is a very smooth melting of the color in your brush into the background picture. You can't do that with an 8-bit frame buffer, however. There aren't enough colors to make all the combinations between the color you've chosen and arbitrary colors in the frame buffer.
Is that going to look like an airbrush?
Well, in a sense, some people call that airbrushing, but airbrushing is really different from that. Airbrushing not only has a shape to the brush, probably a Gaussian shape, but the pixels it's not continuous, it's a random, it's also a distributed. So if you used a brush that, you could do that, I mean, you can do that, you can do anything you can describe. Have a Gaussian distribution of points with a Gaussian envelope of intensities, or whatever the, yeah, I guess it's Gaussian in 3-space, the 3-dimensional version of this thing. And then do this lerping method of painting. I'll use the term lerp a lot. We do it so often we've given it a name. It stands for linear interpolation. Alpha A plus 1 minus alpha B, where alpha varies from 0 to 1. When alpha is 0, you have B. When alpha is 1, you have A. And when alpha is in between, you have some combination of the two. In fact, a linear interpolation between the two. It's probably one of the most basic graphics operations. We use it so often, give it a name. It's lerping. What I just described was lerping a color into the frame buffer using the values in the brush as the alpha. Okay. Other examples of lerping are cross dissolves from one picture to another. You just change the weight alpha constantly, and you, pixel by pixel, use the same alpha. And you get a cross dissolve as you increase alpha from 0 to 1. Yeah?
The users can write functions that say that describe what the modification is going to be.
Sure. Sure.
How does that get linked in?
Well, it's whoever writes the paint program links it in typically. I imagine as these paint programs become more sophisticated, there'll be a mechanism for taking in an arbitrary user's function. In fact, I was just thinking about that on the way over here today. How am I going to do that? We are, of course, going to write a new one at Lucasfilm. We have Tom Porter there, who, short history is the paint program I wrote at New York Tech got sold to Ampex, who modified it. A fellow named Tom Porter modified it, and it came out, is now being sold as the AVA, Ampex Video Art System. Both of us are at Lucasfilm, so we are going to write a super-duper paint program. Today, in the last 3 days, there's been the National Association for Broadcasters, the NAB convention in Las Vegas. 10 paint programs were on sale there at this time. There's only been one before AVA was out last year, but this year there are 10, including one by Dick Schaup, who was the guy who taught me how to do paint programs many moons ago. Okay, back to airbrushing. To really do an airbrush right, you have to not only do the weighting and the distributions correctly, but you also have to simulate the slant of the brush, because the cross section, you can think of it as you change the slant, you take different cross sections through this form. I believe I've heard of at least one place that's done a complete simulation. I suspect it's fairly slow, because you have to do a lerp, which is costly at each point, besides the other computations. Another thing you can do, in fact, when Paul was painting the symmetric face, he was doing what's called filter painting. Under the brush, he was computing at each pixel a local average. And in fact, it was the average of the colors around the pixel using this weighting, 121, 242, 121, to come up with an average value which got reinserted into the pixel whose neighborhood was being averaged. If you have a smooth color map, that tends to smoothly meld one color into another. If you have a random color map like Paul had, it does something interesting, but hard to describe. Depends on what colors have been mapped to your values. In an RGB frame buffer, you get smooth averaging of one color into another. Okay.
Has anybody tried painting in 3 dimensions?
I sure thought about it, and I think it can be done. I don't think I've ever seen it yet. I don't see why it seems like a fairly easy idea if you have, well, I mean, we'll do it. If you have a cylinder out there or some shape that's fairly simple, because you don't want to, paint programs have to be fairly fast because you're keep up with a human fast anyhow. If your paintbrush starts lagging behind you as you paint, it feels so nasty that you probably won't use the program. And I think painting in 3D might be a little too costly unless you have special hardware, because you'd have to take the definition of your surface and the information about where you're painting and have that wrapped onto that surface and displayed fast enough to see where you are. Well, the display of anything in 3D in color is not easy. Yeah. Might be able to use a Evans and Sutherland color picture system to at least outline where you are and perhaps indicate the color.
You want 2 visual fields, maybe one.
Yeah, you'd want the flat one and the wrapped one, right? Yeah, I think so. Okay, now, I think I had fill next, though. Let's talk about filling next. I have 3 videotapes I want to show you. Filling, well, you saw Paul do it in one place. He drew an outline of cloud. He touched white, touched the area enclosed by his white outline, and filled right up. That's the way fill is usually used to color a connected area very quickly and perfectly. That is what I call simple fill. The edges are hard. There's no notion of a slope, a gradual. The white at the edge of that cloud did not meld smoothly into the blue. It was just white blue, sharp edge, very easy to detect. And an algorithm to fill such a connected area is trivial. And in fact, it's probably been reinvented. The algorithm to do that, or algorithms to do that, have probably been reinvented for a couple of decades at least. There are wrong and right ways to do it. There is an algorithm in Newman and Sproul which is recursive, and it's very cute, but it's very slow. Basic notion is quite simple. Draw over on this one. Let's take a very crude picture, and we've blown it way out by a factor of, say we've punched the magnify by 200 button, and we're looking at the scan lines. And everything I'm outlining you can think of as the picture, and everything outside it is the background. Whatever. Okay, this is all background out here. Let's make this a little nastier in connectivity. Just has to be connected, but it doesn't matter what its connectivity is. The idea is I'm going to choose a color, and I'm going to touch a pixel, say that one right there. Call that the seed point. And some algorithm has to figure out that all these other pixels are attached to it, are foreconnected to it, and change their color. Well, I think you can see that's fairly simple. For one thing, you can subdivide this picture into its scan lines. Yeah, my picture didn't come out too well, but I think you get the idea. And you can think about it in several ways. One is you can think about each one of these scan lines being a node of a graph, and the nodes are connected if there are any 2 pixels sharing an edge on adjacent scan lines. And then go into graph space and do a graph traversal of some sort. It's almost as easy just to look at the picture and see what you have to do. I could proceed to the right, and every time I see a pixel which is of the color of the original pixel, I just change its color. And when I finally find a pixel that doesn't have that original color, that's the edge. Okay, so we fill out to there, and we fill out to here. That gets that line. Now I have to find out which pixels were foreconnected to this scan line. Well, that's simple. I just run along above, one scan line above, I only have to run out to the, I call this the shadow. The pixels that are in the shadow of the scan line I've just filled are the only ones I have to look at, obviously for connectivity. So I go zipping along there, and the first pixel I find that's connected, I put it on the stack. And I go along, and so long as I stay connected to that pixel I put on the stack, I don't have to put any other pixels on the stack. Do the same thing for the scan line below, so I probably put this pixel on the stack. Then I start popping the stack and repeating the operation. And that'll get it. I think that's fairly convincing. There are several ways to speed this algorithm up. It's fairly obvious that see, I fill this line. Suppose I pop this point next and fill that. Well, there's no reason to scan above it because I've already filled that. So you can, with a few simple tests, you can just do either scan one line below or scan one line above to find connected seed points. This algorithm will not handle nicely things like putting texture into the area. Some people like to do it'll do texture fill so long as the texture you're putting in does not have the value that you're checking against in it. Now, with a little fancier bookkeeping, you can take care of that case also. Yeah.
In this case, if you had a polygon that was the same color but a different polygon and touching the original one, it would spill over.
Yeah, well, what would it mean? If you had another polygon right here touching, there wouldn't even be a notion of touching. Once it's been rendered into the frame buffer, you've lost the notion of its polygon hood, right? And if it were carefully rendered polygon, anti-aliased in other words, have you talked about anti-aliasing yet, I hope? Don't even consider writing graphics algorithms that don't have anti-aliasing. The days of the Jaggies are over, we hope. It's a lot harder, of course, to write the anti-aliasing in. For example, this algorithm doesn't have anti-aliasing in it. It doesn't know about anti-aliasing. Its extension to anti-aliasing is what I call Tint Fill. And the notion is that these edges aren't hard. They are anti-aliased, or they've been scanned in from the real world, and there are slopes here of color. How do you do that one? Let me show the videotape. I think it'll kind of go through this and some examples, and then it'll cut over to Tint Fill, and perhaps by showing is easier than explaining, although I will talk a little bit. Okay, let's have the fill tape.
Have to worry about anti-aliasing if you got 2,000 lines of resume.
Oh, yes, you do. Yes, you do. You can see if you don't use sampling theory correctly, it doesn't work. Yeah, and you're still sampling even though you've increased the resolution unless you do anti-aliasing. Okay, on my monitor, oh, good. You can see the orange is the area we're going to fill. The blue is the color we're filling with, and the black dots are the points getting put on the stack. After I made this tape, I discovered that there's actually an error in it. I go deep before I go wide, but now, of course, this is a gross simulation of what typically gets filled. An area can be very complex. I believe I have a Hilbert curve on here in a moment, as a matter of fact, that I fill. Just when you write a fill algorithm, you should check it out against a fairly complex, a spiral or something that makes it work. A big convex curve is so easy that almost everything works, even algorithms with bugs in them, even programs with bugs in them. I suppose this is going to be a slower version, or a faster version. These are all created, by the way, frame at a time on an IVC 9000 tape recorder we have at New York Tech, which takes computer-controlled single-frame insert edits. Okay, here's a spiral. it's slowed down. This is much slower than it really goes. This is, I published a paper on fill in a SIGGRAPH several years ago, and I wrote it in a C-like language. And to check out my code, I implemented it verbatim, and this is how fast it goes, just without doing any tricks at all. And I believe the next thing I have in there is assembly-coded version.
How come you got those holes found?
Well, it just hasn't got back to them yet. Those scan lines are stacked. Okay. Okay, I believe what happens next is the real version. No, we're going to do it at about the same speed. Well, anyhow, I use a spiral pattern to check the speed of my algorithms because it slows things down enough that you can actually time them.
Was that Bliss you used?
Bliss? No, C.
You used C.
Yes. Yes, we used Unix and C at New York Tech, and we used Berkeley Unix and C at Lucasfilm. Very, very pleased with it.
Did you go back?
Never. You mean to something before Unix? No way. Oh, that was that. It was called Clear Not Window, and I want to blow it up and let you see what it looks like up close. And that was at real speed. Okay. It's fill code is pretty torturous to decode because you're down the pixel level. Here's a real speed. Here we go. Okay, here's the Hilbert curve. Can you see it filling? Yeah. All right, that one really checks it. Checks your program, checks your code, see if it's really good. And now here's a case to bust it. It's a frame buffer full of random dots, and the stack overflowed right there. You could have put stack checks in there, but the inner loop is so tight here for speed that I left the stack checks out, and you really don't run into the problems very often. This is a variation called boundary fill, where I check for a color of a given color to stop on instead of the fact that I've changed colors. I think I use boundary. This is boundary fill again. Doesn't care what's inside.
Destructive, right?
Beg your pardon?
Destructive, right? All the work that went into putting the highlights in.
We'd saved a picture, though.
Oh.
We'd saved, yeah.
Oh, that's good.
Okay, now this is Tint Fill. This is a demonstration of the much harder algorithm that is filling soft-edged areas. The general idea here is when you fill one line and you fill if you think of black areas as being a low elevation and colored areas as being high elevation, you start at you put the seed point at a point of high elevation, and you let the color flow downhill only. If you ever try to go uphill, then that's the end of your region. That's the definition of the end of the region. So the algorithm is never go uphill, always go downhill. In fact, I started to call it hill fill, but I usually get tongue-tied when I say it. Then you look for points on neighboring lines which the highest point connected to a point that's in the shadow of the one you just filled. It's quite a bit harder thing to check for than in the fill algorithm. This should be a fast simulation. As before, the black dots are the stacked points. Here you have to be much more careful of you have to put the highest points, of course, on the stack, or it won't flow downhill.
What does height mean?
Height means not black. Black is low, and height means away from black. What?
You had blue and red velvet.
Okay, full red would be height 1, full hue, a fully saturated hue. I will discuss those terms in a moment, what hue, saturation, and value are all about. But this is a spiral with soft edges, once again, to exercise the program. It's written in C so that it moves fairly slowly. No, I think that one's moving as fast as it goes. It's just a much harder algorithm to program.
Is it missing pixels? It gets those.
No, it'll get,
Not the ones at the top.
no, it should get all of them.
Gets them there.
Yeah, see, they're just in a funny place in the stack. Yeah. It better not work. I worked in it a long time. I mean, it better not fail. And we're going to blow it up again so that you can see the fine structure. I'm off selecting things on a menu, and I just didn't edit them out. If I'd done a clean job, I would have edited those pauses out. Okay.
What if you have an area that isn't surrounded by something all the same color, and you want to do a smooth fill? Maybe get a red area on this side and green on that side? And fill.
Well, you're talking about, like, here we're always filling toward black. Is that what you mean?
Yeah, or towards the constant
Well,
color.
that's a hard problem. That's what I call RGB fill, tint fill. And it's hard. How do you know where to stop, basically? How do you know you've changed colors? Well, I don't know of any way. You have to threshold. You have to say, okay, that is no longer red, that's orange. And how do you decide? You just have to set a criterion and stick to it. But it's not, I don't know any strong way to answer that question, unfortunately. We're very interested in it.
Get really fast hardware. You just vary the threshold and kind of move the plane up and put some out.
I have a feeling it's color dependent, though. It's not a one threshold that works for all combinations of color. It's probably, yeah. Okay. The next thing I'm going to discuss, in fact, is color. Color is, there are several demonstrations or actual uses of tint fill. I'll let the tape go ahead and play out. Color is a much more difficult subject than I think most people realize. Part of that reason is because we get, well, you've already seen this demonstration of simple fill. It will be followed by some tint fill in scanned-in animation. We have, at New York Tech, there was a whole group of conventional animators who adapted to techniques we provided them on the computers. One thing we provided was a method of scanning in pencil drawings. So they did all the animation on paper, and only the tedious, what they call opaquing, is done on a machine. But opaquing, if you've ever done it, is one of the most incredibly dirty, boring jobs you've ever... I did it for a week just to see what it was like, and it was awful. I can't believe people do it. With a computer, you just touch a color, touch an area. You never go over. If the color's wrong, you just change it. You don't have to redraw the cell. Okay. And another nice thing is in conventional animation, you're restricted to a certain number of levels because you're laying pieces of celluloid atop one another. And although they're transparent, they lose a little light through each layer. So the color has to be modified depending on which layer you're painting on. Not so in the computer version, infinite number of levels, and same color can be used on any level. Now that palette that pops up every so often, somebody had to set that up at some time. How do we go about doing that? That happens to be Paul Zander's favorite set of colors. He just monkeyed around until he got that one, and he used it from there on. Some of the rest of us change palettes every time we do another picture. Just have a bunch of them stored away, just like paintbrushes, hundreds of them stored away, and you just say, I'd like to go work in that part of color space, and you yank it in and use it. One way is to go in and for each paint pot, set the color for that paint pot with red, green, and blue sliders. All right, now here's a scanned-in picture where we use tint fill. You can see it slows down substantially from simple fill, but much faster than opaquing.
by using a shorter palette here.
Yeah, the reason for that is because this is an 8-bit frame buffer. I think the palette had 16 values on it, 16 values, 16 colors. All those colors have to be ramped to black in order to take care of the shading, and that exhausts the color space, 16 shades of 16 colors.
Tell me, you said that at Lucasfilm they were investigating doing films directly from computer graphics. Is that right? I thought they were going to do storyboards, but
We're going to do about everything digital you can think of in a filmmaking process. Audio, editing, mixing, compositing, blue screen matting, synthesis of 3D objects, camera control, bookkeeping, storyboarding, you name it.
so Deck loves
Supposed to like all our customers. Yes?
Just back to maybe that thing about the colors. I mean, eventually we have enough resolution, we can dispense with the film altogether. We have satisfactory resolution and frame buffer and item. But what about the certain qualities, the difference in film and video as far as looking at it?
Well, we have to master those differences. Figure out what they are first, and then do something about it if we can. Yeah, there's very definitely a different look. It's not. It has to do with one of them's a different media. One of them's electronic. You're looking at the light, and the other one's recorded light in chemistry, in chemical emulsions. One of the things we think we'll be able to do is increase the saturation that you see on film. Color saturation on film is very low because every time they print down, time for tape change here, so good time to talk about this. Here, the NTSC is the National Television Standards. In fact, since we're talking about color right now, I'll just put it in the lecture. NTSC is a way of encoding color information into the small channel provided to television broadcast. It's not enough to carry full color. So essentially it's a rounding off of the high frequencies. You run things through a filter, throw away the high frequencies and fit what's left into the allotted bandwidth. But the result is you lose a lot of the color that was in the original pictures in the space we worked in, which was RGB, unencoded color. That space is so important, however, the NTSC space color space is so important, and we'll talk about a little bit here before we finish up. Before I get there, I'd like to talk about hue, saturation, and value. One way for Paul Zander or anybody to set the color of a paint pot is to say, okay, I want to change the color of that paint pot, and pushes a button that says color maker, say, on the menu. And he might get something like this on his menu screen, not the color screen. I get 3 sliders, and they could be horizontal or they could be vertical, doesn't matter. And as he moves red, green, and blue, and as he moves his stylus on the tablet in the area corresponding to this displayed area, well, a cursor probably moves up and down with him. So it's equivalent to having a stick, a lever here that he's moving, or a slider that he's pushing back and forth. And since this is a color map system that we're talking about right here, probably, he will see the color. Every pixel that has the value that he's chosen will change colors in real time as he slides these sliders. So he can change the red and the green and the blue until he gets the color he likes, and then he says, that's it. That gets stored in his palette. Then he can go to the next color, 256 times. A little tedious. So, of course, people have put in ways of generating ramps. You set the endpoints of the two paint pots, this one and this one, and you set the color of this one to red and the color of this one to blue, and then all the mixtures in between get set. A lot of ways of getting colors into a color map. The only thing wrong with this is having to think in terms of red, green, and blue. Most people, especially when they just get started in color, have a lot of trouble figuring out how to do pink or brown with red, green, and blue.
Especially since they deal with subtractive color.
Yeah, especially if you think in terms of even that, you know, subtractive colors. You can think of the hues as being distributed on a circle: red, green, and blue. The so-called subtractive primaries are just the points in between, so it's not very hard to switch your mind over into that space if you want to.
But the mixture works differently if you're looking at things, right?
That's right, because it's absorbing instead of emitting light. It's all the difference in the world. Yeah. But you can map one onto the other. But you're right. Mixing pigments is incredibly much harder than mixing electron guns on a tube. I won't even try to touch that subject because that's art. You just have to know what different pigments do in different combinations. They don't follow linear laws. The nice thing about electron guns on a RGB monitor is they are linear. They do follow linear mixing laws. The mixing is linear. The color space is not linear. In other words, if you move given distance and color space over by the reds, it'll be perceived to be a different change in color than the same distance moved over near green. A space people find more natural to work in is what I call hue, saturation, and value, or hue, whiteness, and blackness space. Go out and find a hue you like, kind of a red or an orange or a purple or a green. You know, hue is probably the strongest psychological component of a color to we folks, to us humans. So I might move this slider up and down, and what I'm seeing now is we move around this color circle, this hue circle. As I move the slider, I see different hues come up. Suppose I wanted pink. Does anybody want to venture a guess on how to get pink using red, green, and blue? What's white? There's no white there.
Red, green, and blue. More red.
All right, so it's going to have red in it, so let's say red all the way to the top. All red, what's that red all the way to the top, and now and these two at the bottom. Okay, now what do I do? You have to pull them all up simultaneously. Okay. Or one way to think about it is you subtract out a DC level of gray. And in fact, the algorithm I'm going to tell you about does just that, to do the hue saturation transform from red, green, blue. Pink in hue saturation value space is trivial. You slide around till you get to red, and then you drop the whiteness, or you increase the whiteness. That's it. It's easy. How do you get brown? Well, set it to red or kind of orangey red and and increase the blackness. What is that here? Well, you can do it once you get used to. I've been going back and forth between the two spaces so long, you can probably just do it in red, green, blue. But part of the idea is so that computer naive people like Paul Zander, the artist you saw working a while ago, doesn't have to know a thing about transform. In fact, I don't believe he would understand ever how to do the transform. You just give him the tools and he uses them. Transform's so easy, I'll just show it to you. Let's see, where is that thing? Okay, overhead projector. Right there. Okay. So this is the algorithm that generates, given red, green, and blue, it generates the equivalent hue, saturation, and value, where red, green, and blue, hue, saturation, and value are all assumed to be on the range 0, 1. First thing you do is take the maximum. The value is just going to be the maximum of the three colors. Suppose our colors, I'll use this set of bars up here twice. You can think of a color as maybe this much red and this much green and that much blue. where this is the maximum any of those three things can be. Okay. Well, the value is just simply the maximum of those three lengths. That turns out to be a measure of the blackness of the color. The saturation is the max minus the min. In other words, take out this DC value, and that relative to the max. In other words, the percentage of this distance to the maximum distance is the saturation. If we had pure red, no green and no blue, then it's a fully saturated color. Fully saturated, meaning it's all there. The hue is what's left over after you take out the DC level, take out the gray. In other words, it's some mixture of two primaries. A hue is a mixture of two primaries. And as another way to see that is that circle I drew a while ago, red, green, and blue. No blue, red, and mixtures of red and green takes me through this part of the circle, so forth. So a color is a mixture of three primaries. A hue is a mixture of two primaries, and a primary is a mixture of one primary. Okay. There are other similar definitions, similar transformations. You'll hear frequently hue, saturation, and brightness, or some such term. Hue, chroma, and brightness is another. In fact, there are a lot of confusing terms out there. That's why I'm tending more and more to go to whiteness and blackness, because people tend to mean something by saturation and value that they learned in another theory. It shouldn't be brought over to this very simple color space theory of the color space of an RGB monitor. Just to put some of this in perspective, let's, while we got the overhead projector there, let me just show you the inverse algorithm. It's also trivial. What's nice about these algorithms is they're very quick and dirty. You just don't hardly take any. And so a person can work in hue, saturation, value space, hue, whiteness, blackness space, and the computer can translate in red, green, blue very quickly.
What's K?
It's defined here somewhere. I don't know. It's K is it's just three numbers that are being defined right there. It's a BCPL type structure where you say let, that means define a variable whose name is M and give it this value. Yeah. The color space we're talking about is the human color space in general. The human color space, the gamut of colors that human beings can perceive, is a very irregularly shaped blob in color space. There are a lot of ways to represent it, but perhaps the best to tell you about is the CIE standard gamut. CIE is it's French. Commission Internationale d'Éclairage or something like that. It's the International Council on, or Committee on, or Commission on Illumination. This is the famous CIE chart. What it is, it represents every color that a human being can perceive. It's based on measurements of human beings. It's not as you can see, it's not a nice geometrical photonic solid. This locus right here contains all the pure spectral colors. You diffract a white light through a prism, those points will lie right along here. All other colors lie inside. The whites are somewhere in the center, more or less. There are a lot of different whites, by the way. White is a difficult thing to define. It seems to turn out to be the brightest thing in your field of view. Becomes white sooner or later. Later, mostly, after you've adapted a while. Now, this is just a two-dimensional representation. All of the brightness information has been factored out of this chart. So we just have, it's kind of like the hue and saturation are now left, but it's a little That's a very sloppy analogy, but as you go around here, you go through the hues, and as you go out from the white, you increase saturation. Okay. The subset of this space that we deal with an RGB monitor looks about like this. Okay. A lot of the colors human beings perceive can't be seen in TV. Doesn't seem to bother us much, but now you asked about film a while ago. Film is something like this. Okay, it's a different subset of human perceptual space, but it once again is not the entire thing, and it doesn't coincide, unfortunately, exactly with video's color space. So a lot of the problems that we at Lucasfilm encounter, for example, is how do you compensate for the difference? You work in this nice triangular linear mixing space of video. You want the results to be transformed unchanged into film space. Well, clearly you can't do it perfectly. How do you do it? Well, it's a difficult problem. We won't talk about that today. Yeah.
Is that TV triangle because of the fringe thing of the art, or is that the
No, that's because there are three guns. There are three phosphors on the face of the tube that emit light, and the locations in CIE space of those three phosphors are these places right here. The red, you can see, is almost a perfect red. It's a spectrally pure hue. Blue's good, but green is not so hot. It's kind of yellowish.
Has anyone tried to change phosphorus?
Yeah, you see different. In fact, the original in 1954, 53, when the NTSC first set up and tried to standardize what color TV was going to be, way before they should have. Yeah, the Fortran of their times. Let's see. They came up with a space something like this. So that's what it was based on phosphors of the time. Well, it turned out they found much more efficient phosphors, so we have much brighter pictures on our TV sets now. But we had to sacrifice color for it. So this smaller triangle, which you'll see these are all greens out here, by the way. Most of nature's greens that we perceive as humans, we don't see on television or film. These are the yellows, and these are the deep purples. Yeah?
Using like a laser scanner, can you get better colors?
Well, that's what we're going to do. We're going to use lasers over there, and the notion is that we can undo the loss of color because of crosstalk between the dye layers of the film. But it's still the film, so you can't do any more than the pigments are capable of. I mean, we can't get a color out here. It's just not there. It's not available. Yeah.
But you can correct for the color bias in the film itself, can't you?
Yeah, sure. That's what we'll try to do.
It's interesting to see that if you do succeed in making large changes in colors in films, that we don't go through a syndrome like they did when they first had 3D things, that all they made was movies where things jumped out at you. You know?
That's a problem with all the computer graphics, in fact. One of the most trivial things you can do with a color map is cycle it. And everybody who hasn't seen one gets off on it. But I tell you, I've seen so many cycling color maps, I am disgusted when I see one now.
If they improve color drastically, they may never do a scene in the dark for years and years.
I'm sure we're not going to take over that way. The film people have quite a tradition, and actually we have to crawl in and beg to be used in their movies. It's not like they're jumping out to grab this new stuff. We've still got a lot to prove.
On the other hand, you can use it all you want in your Star Wars movies.
Well, we've got to convince our own people that they want to use it. It's, you can't just, there are a lot of problems to be solved, is what I'm trying to say. You can't just jump in and start, you got to anti-alias everything. And you've got to mix it in with live action. You've got to have the lighting look the same. You've got to have the green noise look the same. And the color saturation not overwhelm that in the other parts of the movie filmed different ways. There's lots of problems.
Will you be getting more saturation than real life? Sometime?
No.
No.
No. Real life saturation is pretty good. Real life is out here. You'll notice none of...
No. Sorry,
what?
real life on film.
Oh, yeah. Yeah, that's what I mean. We should be able to improve the saturation you see on film.
How are you gonna push it? Because it seems like you're only restricting yourself.
Well, film has 3 layers. Color film has 3 layers. At least 3. Has a lot more, actually. They're just gooey chemicals. And even though they say they fix it, it never really stops. And over time, these chemicals migrate through. In fact, you keep hearing about how color films are losing their color. That's why they lose their color. And every time you print one piece of film onto another piece, for example, you record in negative film, but you release and print in positive film. That's a printing step. There's crosstalk. Since these three things are all, the light that does the recording on another piece of film goes through all three layers. So there's a crosstalk between the three layers. And you have to have some ingenious technique to undo that crosstalk. Conventional film techniques cannot undo it.
Like Technicolor and things like that used to do three separate.
That's the way they took care of the problem.
Yeah.
Yeah. It's very expensive these days with silver prices being what they are. The most sophisticated, there's only one sophisticated Technicolor lab left that I think of, that I know of. The most sophisticated is in China, I believe, oddly enough. Yeah. This is in two-space, yeah. Well, they're called X, Y, and Z. Capital X, capital Y, capital Z. They're just defined. They're not even real primaries. They exist outside the space. Doesn't matter. It's just a linear transform. Get you inside if you want to. They chose these because then all colors have positive coordinates, which seemed like a nice idea. Okay. Now there's one other. We're running out of time rapidly here. Color can go on for a long time. There's one other space I'd like to tell you about because it's so important, and that is the color space of NTSC television. It's YIQ space. Now, YIQ space is a transform of, it's just a straight 3x3 matrix multiply of RGB gets you YIQ. And instead of writing it, we'll look at it on the overhead. Okay? It's the matrix in the center there. The most important one being the Y equals, it ought to be 30% red plus 59% green plus 11% blue. That's so-called luminance. That's what gets broadcast over a black and white television set. And that, in fact, is why they chose that particular matrix. One of the reasons is because it twisted things around. It transformed the space such that one of the principal axes contains all the brightness information, and which happens to be the most important component. You can throw out a lot of the color, but you can't throw out the brightness. So the full bandwidth of television, color television, is allotted to the brightness, or luminance is what it's actually called. This is called luminance. It's pretty much associated with what we perceive as brightness. The I and Q axes are the color, contain all the color information. I stands for in phase and Q stands for quadrature. It's old terminology. Why don't we look at the color tape to take it on out? Here. They can't see this at home. Here's one. This is YIQ space.
Is that an RGB monitor?
It's off of a color monitor, RGB monitor. In fact, all this tape you'll see, it's a very fast run-through of some of the things I've said here. It shows the CIE chart. It shows the NTSC gamut superimposed on it. It shows a deformation of that space into a so-called uniform color space. Nobody's found a perfect way to do uniform color spaces, and uniform means that equal distances are equal perceptual differences. A special set of color bars. This is just some Wowie Zowie graphics based on a color solid that I was programming up. This happened to be the model of the hue saturation value space, the so-called hex cone space. Same. That was the RGB color cube taken through a few turns. You can't do this on an 8-bit frame buffer. Uh-oh, I said it, and there it is, cycling color maps. No, actually, this is quite a bit fancier than simple cycling. This is bouncing, where you can think of a ball bouncing around inside of the color cube, the RGB color cube, and it's leaving a trail of colors behind it as it bounces off the walls, and those colors are getting shifted into the color map. So, and it bounces in a random direction when it hits the walls. So it's at least one step beyond It's got randomness in there too. Okay, here's an explanation of the terms I've been using. White and black combine to make grays. Hues and blacks combine to make shades. And tints are whites and hues. And a tone is a mixture of all three of those. Once again, definition of hue, saturation, value, the color bar interpretation. The background here is the color of the foreground of the gun set proportionally to the foreground bars. Well, yes, because of the transform here, you can take HSV, transform it into RGB, matrix multiply it into...
Is the IYQ sort of more conceptually the same as HSV?
No, not really. It's more conceptually the same as RGB. It's just a linear transformation of RGB space. This is a random color map, and it's going to be sorted. It's being sorted by hue. You can see the hue starting to line up on the right side.
What sorting algorithm are you using?
It's a bubble sort, so it's fun to watch. Yeah. Slow but fun. Quick sorts are too fast. This is, you can guess.
The circle, the RGB circle, right?
Yes. Now this is the hex cone, that is the hue, saturation, and value color solid, the one that's naturally associated with it, just being flown around in space and dropping the value as it flies. Same thing with this joint. Each plane there is a plane of constant value. Seen head on. You can see why it's called a hex cone, by the way, I think. Okay, here we are moving out in saturation from the center, which is completely desaturated. And then as it flies away into space, we're decreasing the saturation, so the surface is the locus of decreasing saturation. This is we're plane of constant value increasing the locus. Now this is an example of painting in an RGB frame buffer. I'll choose a hue off the palette and modify only the hue in the frame buffer, okay? So you'll see the darkness preserved. In fact, I might be... No, this version I don't believe is keeping the whiteness. But you can do that one too. One of them's called hue painting, the other one's called tint painting. The background here, by the way, was generated with a function and taken through some fancy matting turns. Okay, that's about what I have to say today. Is there any questions?
How can you stand doing such boring work?
It's a nice job. Yeah.
We only have the CIE color solid here.
Oh yeah, it'll be up in a minute. Now this is a case where I'm having to do an RGB HSV transform at every pixel, so it's very important that the transform be very fast, or you would feel it. In fact, you could feel it in that program. It was just a little too slow to be nice. Some more art that just happened to be in the frame buffer while I was debugging the color solid program. First thing painted with the new RGB paint program. Another thing. That's CIE. Okay, with the Barco, this is made on a Barco monitor. That's the deformation into a uniform perceptual space. You'll see that it's actually a better picture of what colors aren't represented. This looks like an amazing number of greens aren't available, but when you put it in uniform terms, it doesn't seem like so many are missing. That is the printer's ink gamut, the irregularly shaped one. A uniform version. Okay, here we're growing the YIQ polyhedron, looking straight down the y-axis. These are planes of constant luminance, and I'm turning off the color so you can see that indeed the luminance is constant. See? See what you miss when you have a black and white set? It shouldn't. It shouldn't. Yeah. Okay, this is seen down the other two principal axes. They were chosen, by the way. One of them contains the flesh tones, and so it was given a little more bandwidth than the orthogonal axis, which doesn't, the one orthogonal to the flesh tones. And when I kill the color, you'll see that the luminance indeed decreases smoothly from top to bottom. On your black and white monitors, you should see that already. That's right. That's right. It actually was a clever engineering solution. The NTSC standard was quite clever because they were forced to fit a very wide signal into black and white channel, and they did it surprisingly well. Those of us who work with RGB, they'll cry every time we see our signal. It's very important when you're choosing colors for television, for an animation that might appear on television, that you choose colors that do look right on a black and white monitor, because that's all some people have.
What about all the 2 or 3 other big formats in the world, as far as what they offer?
You mean PAL and... PAL is essentially the same color space as NTSC. Well, really, they all are, because they have to end up on monitors of similar manufacture. This happens, what you're seeing here happens to be a model I didn't discuss. It's a conversion of the YIQ space into hue, saturation, and value terms, hue, saturation, and brightness terms. If you normalize, if you use this axis, if you use this definition to normalize your any given 3 colors, what's left is a triangle with its centroid off center. This is the YIQ cube hit polyhedron, actually turned on its main diagonal and wrapped out onto this flat surface. And that's where the work was done. Yes?
Does the TV, you see the broadcast signal pick up on I value and then translate that back to an RGB and display it?
Yep, that's what it does. It actually it strips off the signal off the carrier, and
that's why they say that it's encoded as a phase angle.
yeah, it's encoded like this. The modulating signal is the Y signal plus the I signal times cosine omega t plus Q signal times sine omega t, where omega is the phase angle. Yeah, I might have those reversed. And they've also been gamma corrected, which is something else I didn't talk about, but you gotta, these tubes aren't linear, so you have to undo the nonlinearity. Okay, folks, thank you.